Welcome to Scientific Serenity. Tonight, we close our eyes, not just to rest, but to enter a world that has puzzled philosophers, scientists, and dreamers for millennia. A world that begins the moment our eyelids shut out the light. This is not a story of superstition, but of science. A story of how humanity discovered one of its most intimate, universal, and mysterious experiences, the cinema of the sleeping mind. This is the story of REM sleep. But before we arrive at the cold, fluorescent light of a 1950s Chicago laboratory, we must journey back, far back, to a time when the night was not measured in EEG squiggles, but in myths, omens, and divine whispers. To understand the shock of the discovery, we must first understand the depth of the mystery. Imagine a world without electric light. Darkness is absolute. The only sounds are the crackle of a dying fire, the call of a night bird, the rustle of leaves in the wind. In this profound darkness, humans slept, and in that sleep, they journeyed. They flew without wings, spoke with the dead, fought monsters, loved strangers. They awoke with memories so vivid, so emotionally charged, that they could not be mere imagination. They felt like visits, messages, prophecies. In ancient Mesopotamia, over 5,000 years ago, dreams were considered direct communications from the gods. Clay tablets record detailed dream interpretations. A dream of flying might predict escape from danger. A dream of losing a tooth could foretell the death of a family member. The dreamer was a passive recipient of divine intelligence, a clay tablet upon which the gods inscribed their will. In ancient Egypt, dreams were a state of heightened spiritual receptivity. Temples dedicated to the god Serapis functioned as incubation chambers. People would sleep in these sacred spaces, hoping for a healing dream or a divine prescription from the god. The line between sleep, medicine, and religion was invisible. The dream was a doorway to another, more powerful realm. The Greeks formalized this belief. In Homer's Iliad, dreams are personified as winged beings who descend from Zeus to deliver messages to sleeping kings. Later, in the 2nd century AD, the philosopher Artemidorus wrote the Ionaria Critica, a 5-volume dream interpretation manual that would influence Western thought for centuries. But it was the Greek physician Hippocrates who first suggested a more physical origin. He proposed that dreams could reflect the state of the body. An excess of bile might cause nightmares of fire and conflict. This was a faint, early glimmer of a materialist explanation, a tiny crack in the supernatural edifice. This crack widened slightly in the Enlightenment. As science began to dissect the natural world, dreams were demoted from divine messages to neurological noise. In 1899, Sigmund Freud published The Interpretation of Dreams, a book that would redefine the conversation for the 20th century. For Freud, dreams were not divine, but deeply human. They were the royal road to the unconscious, a scrambled theater of repressed desires, childhood memories, and primal conflicts. The content was symbolic, a code to be deciphered by the analyst. Freud's theory was revolutionary because it placed the dream squarely within the individual's mind, not in the heavens. But it was still a theory of meaning, not mechanism. It asked why, not how. It was psychology, not physiology. While Freudian analysts were listening to patients recount their dreams on velvet couches in Vienna, a very different kind of scientist was beginning to ask a more fundamental question. What is sleep physically? Not psychologically, but physically. What happens to the body when it slips from wakefulness into oblivion? The early 20th century saw the birth of sleep science as a physiological discipline. The key tool was the electroencephalogram, or EEG, invented by the German psychiatrist Hans Berger in 1924. For the first time, scientists could see the electrical chatter of the living brain. Berger discovered that the brain's electrical activity changed dramatically between wakefulness and sleep. The busy, fast, low-amplitude waves of the awake state gave way to slower, larger, more synchronized waves as a person drifted off. This was objective proof that sleep was not a uniform state of nothingness. It had stages. It had architecture. Other physiological measures followed. Scientists began recording our movements, muscle tone, heart rate, and breathing during sleep. They were building a multi-instrument portrait of the sleeping body. Yet, the dream remained elusive, a ghost in the machine. It was considered a mental phenomenon, inaccessible to the crude electrodes and numographs of the time. The prevailing wisdom in the 1930s and 40s was that dreams, if they occurred at all, happened in the fleeting moments of awakening, or in a very light, almost waking sleep. The deep, slow-wave sleep revealed by the EEG was thought to be a period of mental blankness, a time when the brain was truly off. This was the scientific landscape in the early 1950s. Dreams were the territory of psychoanalysts. Sleep was the territory of physiologists. And the two worlds rarely spoke the same language. The brain was a black box. You could measure its electrical output, but you could not see inside. The mind was a separate, shadowy entity. The idea that you could pinpoint the precise physiological moment of dreaming was considered laughable. Dreaming was subjective, fuzzy, unscientific. It was into this divided world that a young, slightly insecure graduate student named Eugene Aserinsky walked. He was not a star. He was a man in his early 30s, a former dental student, a soldier, now trying to find his footing in the nascent field of physiology at the University of Chicago. His advisor was the formidable Nathaniel Kleitman, a pioneer of sleep research and author of the seminal 1939 text, Sleep and Wakefulness. Kleitman was a rigorous, no-nonsense scientist. He believed in data and meticulous measurement. He was skeptical of Freud and the soft science of the mind. Aserinsky's initial assignment had nothing to do with dreams. He was tasked with studying the eye movements of sleeping infants, thought to be related to learning. The equipment was crude. To measure eye movements, he used an old polygraph machine, its pen scratching on rolling paper. The electrodes were clunky. The subjects, his own infant son, Armand, and later other babies, would often pull them off. It was tedious, messy work, but in the midst of this tedium, Aserinsky noticed something odd, not in the infants, but in the control recordings he took of adults, including himself. Periodically, during what was supposed to be deep sleep, the pens tracking our movement would go wild, scribbling frantic back-and-forth patterns. This was not the slow, rolling eye movement believed to occur at sleep onset. This was rapid, jerky, almost violent movement, and it would last for minutes at a time. At first, he assumed it was a malfunction, a loose electrode, electrical interference. He checked and rechecked his equipment. The signal persisted. Then, he looked at the EEG channel recorded simultaneously. He expected to see the large, slow waves of deep sleep. Instead, he saw a low-voltage, fast, desynchronized pattern, a pattern that looked identical to the EEG of an awake, alert person. This was impossible. According to the textbooks, the sleeping brain was supposed to be quiet and slow. This brain was awake, but the person was unmistakably asleep. Aserinsky had stumbled upon a paradox, a brain awake in a sleeping body. He had no idea what it meant, but he knew he had found something big. And he knew he would have to convince the most skeptical man in the building, Nathaniel Kleitman. As we leave this opening chapter, poised on the brink of that discovery, let the ancient mystery of dreams settle around you. For thousands of years, dreams were voices from the gods, symbols from the unconscious, meaningless static. In just a few years, they would become data points on a polygraph roll, a physiological state as measurable as heart rate. The journey from temple to laboratory is one of the most profound in human thought. But tonight, you are not in a laboratory. You are in your own temple of sleep. As you listen, feel the weight of your own eyelids. That simple act, closing your eyes, is the switch that begins the ancient, personal ceremony. Whether you remember your dreams or not, that ceremony happens. Your brain has its own script, written in a language of electricity and chemistry, waiting for the curtain of consciousness to fall. Let that thought comfort you. You are about to embark on a voyage that every human takes, every night of their lives. And for the first time in history, we know the map. We know when the ship sets sail. Aserinsky's first instinct was not excitement, but anxiety. In science, the most common response to an unexpected result is not eureka, but what did I do wrong? He meticulously recalibrated the polygraph. He changed the electrodes. He tested on different subjects. The phenomenon persisted. There, in the dead of night, in the quiet lab, the pens would suddenly skitter to life, tracing their frantic dance for 20, 30, sometimes 40 minutes before falling silent again. And each time, the EEG told the same baffling story. A brain lit up like a city at night, while the body lay still in the depths of sleep. He tentatively brought his findings to Kleitman. The older scientist was, as expected, deeply skeptical. Kleitman had spent decades mapping the steady, predictable landscape of sleep. He had documented the progression from light drowsiness to deep, slow-wave slumber. This erratic, wakeful brain activity in the middle of the sleep cycle did not fit the map. It looked like an artifact. Perhaps the subjects were partially waking up. Maybe the EEG leads were picking up muscle activity from the eyes themselves. Kleitman urged caution. More data. More controls. This period was a crucible for Aserinsky. He was a graduate student, his career uncertain, up against a fundamental paradigm. To prove this was real, he needed to rule out every other possibility. He designed a simple but brilliant control. If the subjects were actually waking up during these episodes, they would be able to respond to external stimuli. So, during the periods of rapid eye movement and awake EG, he would gently speak the subject's name or make a soft sound. No response. He would touch them lightly. Still no response. The subjects were profoundly asleep, even as their brains blazed with activity and their eyes darted beneath their lids. The next question was the most tantalizing. What was happening in a mind during these periods? The physiological signature was clear, but the mental content was a black box. The only way to know was to wake people up and ask. This introduced a new layer of complexity. Waking someone from deep slow-wave sleep typically results in grogginess, disorientation, and few, if any, mental impressions. But what would happen if you woke someone during these peculiar, active sleep periods? The first subjects were, again, Aserinsky himself and a few brave volunteers. The protocol was grueling. They would sleep in the lab, their heads wired like modern-day oracles, while Aserinsky monitored the polygraph rolls. When the pens indicated the start of a rapid eye movement period, he would wait a minute or two, then enter the room, turn on a light, and gently wake the sleeper. Immediately, he would ask, "What was going through your mind just now? Were you dreaming?" The results were striking. When awakened from non-REM sleep, especially deep sleep, subjects often reported vague, fragmentary thoughts, or nothing at all. "I was thinking about the lab," or nothing, just blank. But when awakened from REM sleep, the reports were different. They were detailed, narrative, emotional, visual. "I was being chased through a forest." "I was talking to my father, who passed away." "I was trying to solve a puzzle that kept changing shape." The correlation was not perfect, but it was strong. The active brain state, the rapid eye movements, and the experience of dreaming were converging. Aserinsky and Kleitman began to see the outline of a radical new structure. Sleep was not a single, descending staircase into unconsciousness. It was a cycle. A person would drift down through the stages of light sleep into deep sleep, then ascend back toward light sleep. But instead of waking up, they would enter this new, physiologically distinct state, a state of brain activation, muscle paralysis, They noted the body was very still during REM, rapid eye movements, and, frequently, vivid dreams. Then, the cycle would begin again, roughly every 90 minutes, all night long. They presented their preliminary findings at a small scientific meeting. The reception was muted. Sleep research was a backwater. Dream research was considered fringe. The idea that dreams could be tied to a specific, measurable brain state seemed to straddle an uncomfortable line between hard physiology and soft psychology. It made many scientists uneasy. Undaunted, they pressed on, refining their methods. A key addition to the team was William Dement, a young medical student with boundless energy and a keen interest in the mind. Dement would become the evangelist of REM sleep, but in these early days, he was another pair of hands and eyes in the lab, helping to run subjects and analyze the mountain of data. The culmination of this work was a paper published in the journal Science on September 4th, 1953. The title was deliberately dry, technical, and unassuming. Regularly occurring periods of our motility and concomitant phenomena during sleep. It was a masterclass in understatement. The paper meticulously described the physiological phenomena, the periodic bursts of eye movements, the correlated shift to low voltage, fast EEG patterns, the suppression of body motility. It noted the association with dream recall when subjects were awakened from these periods. It proposed the term rapid eye movement period and suggested these periods were a unique phase of sleep. The paper did not shout, "We have discovered the physical basis of dreaming." But for those who could read between the lines, that's exactly what it said. It was a quiet bomb. It provided a tool. For millennia, dreaming had been a subjective phantom, impossible to pin down. Now, for the first time in history, an external observer could look at a polygraph tracing and say, with reasonable confidence, the person in that room is dreaming right now. The implications rippled out slowly. The first and most direct was that dreams were not random, fleeting epiphenomena. They were scheduled events, produced by a specific, observable brain state that occurred in predictable cycles throughout the night. The brain was not passive during sleep. It was periodically as active as it was during wakefulness. This demolished the old notion of sleep as simple brain idling. Secondly, it provided a bridge. Suddenly, neurologists and physiologists had a legitimate reason to study dreams. They were no longer just Freudian symbols. They were biological events. Psychologists, in turn, could now study dreams with a new precision, knowing when to wake subjects to capture them. The two solitudes of sleep science began to talk. But in 1953, all of that was in the future. For Aserinsky, the immediate future was a PhD thesis and a degree. For Kleitman, it was another data point in a long career. Neither man fully grasped the seismic shift they had triggered. They had opened a door to a hidden chamber in human biology, a chamber where a dazzling, mysterious show played out every night for every person on the planet. As you reflect on this moment of discovery, imagine the scene: the musty smell of the lab, the incessant scratch of pens on paper, the dim light, the sleeping forms, the young scientist peering at the cryptic lines, his heart pounding with a mixture of fear and exhilaration. He was looking at the visible fingerprint of the invisible, the measurable trace of the most private experience a human can have. Let that sense of discovery wash over you now. The mystery of your own dreams is part of a rhythm, a cycle, a biological clockwork that ticks away inside you with the reliability of a heartbeat. You don't have to interpret symbols or search for divine messages to appreciate it. The simple fact of its regularity, its embeddedness in your physiology, is a wonder in itself. Tonight, as you lie in the dark, you are not just a passive dreamer. You are a participant in a biological ritual that science has only recently learned to see. Your closed eyelids are the curtain. The rapid movements beneath them are the overture, and the activated brain, humming in the silent theater of your skull, is the projector, casting its stories on the screen of your sleeping mind. Our journey through the first chapter of this discovery closes not in the glare of scientific acclaim, but in the quiet, personal realization of what it all means. For you, right now, lying in the dark, listening to this story, you are the living endpoint of this long historical and scientific arc. The dreams of the ancient Mesopotamians, the theories of Freud, the meticulous all-night vigils of Aserinsky, all of it converges in the gentle rhythm of your own breathing, in the subtle, hidden movements of your eyes beneath their lids. We have learned that REM sleep is a biological fact, but its meaning transcends biology. It touches the very core of what it means to be a conscious being, a creature that lives in a world of external sensation by day and internal narrative by night. The discovery of REM sleep did not explain away the mystery of dreaming. It simply gave the mystery a physical address. We now know when and in what state we dream, the why and the how of the dream's content, its surreal narratives, its emotional power, its uncanny resonance remain, in many ways, as mysterious as ever. But perhaps that's the true gift of this knowledge. It allows us to hold two truths at once. The first truth is scientific, material, measurable. Dreaming is a brain state. It is a cyclic, regulated, necessary physiological process involving the pons, the thalamus, the amygdala, and the visual cortex. It is characterized by rapid eye movements, muscle paralysis, and an EEG pattern that mimics wakefulness. It is conserved across mammals, suggesting a deep evolutionary purpose. The second truth is experiential, subjective, and profound. Dreaming is a world. It is a private theater where we are both actor and audience, where the laws of physics are suspended, time is elastic, and the dead can speak. It is where we process fear, desire, grief, and joy in symbolic code. It is where creativity is seated, and sometimes where solutions to waking problems emerge unbidden. The discovery of REM sleep bridges these two truths. It tells us that the second, the mystical seeming world of dream experience, is irrevocably tied to the first, the physical world of neurons and neurotransmitters. The spiritual and the material are not at war. They are two languages describing the same miraculous event. As we prepare to leave this introductory chapter and delve deeper into the specific dramas of the Chicago lab, the rise of sleep medicine, and the ongoing puzzles of REM, let us pause to integrate this perspective. Close your eyes if they are open. Feel the weight of your body on the bed. Notice the slight dryness behind your eyelids. This is the threshold. Every time you cross this threshold, you are engaging in a biological ritual that is also a psychological journey. You are not just powering down. You are initiating a sequence of events as complex and orchestrated as a symphony. The first movement is light sleep, the drifting away. The second is deep sleep, the plunge into restorative oblivion. And the third, the movement we have spent this chapter discovering, is the REM movement, the reawakening of the mind within the sleeping body, the solo performance of the brain, playing its greatest hits and working through its unresolved melodies. Tonight, you don't need electrodes or a polygraph to participate in this discovery. You are the instrument. Your awareness is the observer. As you listen, you may feel the first tug of sleep. That tug is the beginning of the cycle. Your brain is starting its descent, preparing for its first appointment with the REM state, roughly 90 minutes from now. Let this knowledge be a source of deep comfort, not of analytical distance. There's a part of you that knows exactly what to do. A part that has been following this script since before you were born. You don't have to make yourself sleep. You don't have to force yourself to dream. You simply have to let go, and the ancient, automatic machinery will engage. Think of Eugene Aserinsky, tired and skeptical, watching the pens jump. He was seeing the outward signature of this inner machinery. He was, in a sense, seeing you. Not you personally, but the universal human process you are engaged in right now. Your dreams are part of the data that proved his theory. Your sleep is part of the phenomenon he helped the world to see. So, as we end this chapter, offer a quiet thought of thanks, not to any god of sleep, but to the curious, stubborn, brilliant humans who spent sleepless nights so that we could understand our own. They pulled back the curtain on the most private of human experiences and showed us the clockwork behind the magic. They gave us the map to our own nocturnal journeys. Now release the map. You don't need to navigate. The journey happens on its own. Let the words fade. Let the concept soften. Allow your attention to sink inward, away from the story of sleep, and toward the experience of it. Feel the gentle pull. Your breathing may naturally slow. Your limbs may feel heavier. This is the descent beginning. You are entering the first stage of the first cycle. The laboratory of your own brain is preparing its instruments. In about an hour and a half, the curtain will rise on your own personal dark cinema. But for now, there's only the descent, the quiet, the trust. the magnificent, silent machinery of you, doing what it has done for millions of years of evolution, and what it will do tonight, with or without your conscious permission. Surrender to it. There is nothing to do, nothing to figure out, only to allow. The discovery has been made. The phenomenon is known. Now it is time to experience it firsthand from the inside. The discovery of REM sleep did not spring fully formed from a single eureka moment. It emerged instead from the gritty, tedious, and profoundly human soil of a university basement laboratory. This chapter takes us inside that laboratory, to the University of Chicago's physiology department in the early 1950s. Here the abstract concept of science dissolves into the tangible. The smell of ozone from electrical equipment, the chill of a room kept cool for the sleeping subjects, the ache in a young graduate student's back from hours of staring at a polygraph roll. And at the heart of it all, a father and his son. To understand the dynamic that led to the discovery, we must first understand the two principal characters. Nathaniel Kleitman was, by 1951, an institution. In his mid-50s, he was the world's foremost authority on sleep. His 1939 monograph, Sleep and Wakefulness, was the Bible of the field. He was a classic empiricist, a believer in meticulous, repetitive measurement. He was skeptical of grand theories, especially psychoanalytic ones. For Kleitman, sleep was a physiological problem to be solved with data, body temperature, motility, brain waves. The mind and its dreams were ephemeral, outside the realm of proper science. He was a stern, demanding, and somewhat intimidating figure, a man who had built his career on the bedrock of slow, careful, incremental progress. Enter Eugene Aserinsky. At 30, he was a man still searching for his path. His academic journey had been meandering. Pre-med, dental school, a stint in the army, jobs in various labs. Now he was a graduate student in Kleitman department, older than most of his peers and feeling the pressure to produce. He was assigned to Kleitman not out of shared passion for sleep, but almost by administrative default. His initial project was modest, to study our movements in sleeping infants, a topic Kleitman thought might relate to nutrition or learning. It was not glamorous work. It was the kind of project given to a student whose potential was uncertain. The equipment was primitive by today's standards. The polygraph was a bulky machine that used ink pens to trace signals on long, continuous rolls of paper. To measure our movements, Aserinsky used a method adapted from studies of nystagmus. He attached small electrodes to the skin near the subject's eyes. These electrodes picked up the tiny electrical potentials generated when the eyes moved the corneoretinal dipole. It was a finicky setup. The electrodes dried out. The paste holding them in place irritated the skin. Infants, as primary subjects, would inevitably fuss and pull them off. It was during these frustrating sessions that Aserinsky made his first, crucial decision as a scientist. He decided to run control studies on adults, including himself. He needed to know what a normal eye movement recording looked like to better understand the infant data. This was standard procedure, but it was in these control runs that the anomaly appeared. Night after night, Aserinsky would wire himself up, start the polygraph, and try to sleep in the strange lab environment. The pens would scratch away, tracing the slow, rolling movements associated with drowsiness, then often going quiet as he entered deeper sleep. But then, something remarkable would happen. Periodically, long after sleep had begun, the pens would erupt into a frenzy of activity, scribbling rapid back-and-forth deflections. This was not the smooth sine wave of a rolling eye. It was a staccato burst, like the needle of a seismograph during an earthquake. Aserinsky's first reaction was irritation. He assumed it was artifact, interference from the building's electrical system, a loose wire, or muscle twitches from the face. He spent weeks troubleshooting. He shielded cables. He changed electrodes. He tested different subjects. The phenomenon persisted, and it had a peculiar regularity. It would happen roughly 90 minutes after sleep onset, last for a few minutes, cease, and then return about 90 minutes later. But the real clue came when he looked at the other channel on the polygraph, the one recording the electroencephalogram, the ED. The brain waves during these periods of frantic eye movement were not the large, slow, synchronized waves of deep sleep. They were low voltage, fast, and desynchronized. They looked, for all the world, like the brain waves of someone who was wide awake and alert. This was the paradox that would define REM sleep. A brain appearing awake, locked inside a sleeping, immobile body, with only the eyes betraying a frantic, hidden activity. Aserinsky knew he had stumbled upon something significant, but he also knew his position. He was an improving graduate student with a formidable, skeptical advisor. To bring this to Kleitman, he needed more than a curious squiggle on a chart. He needed ironclad proof that this was a real biological phenomenon and not an artifact of his janky setup. His first step was to rule out waking. Perhaps the subjects were simply briefly arousing, opening their eyes and looking around. He devised the simple wake-up test. During the periods of rapid eye movements, he would enter the room and call the subject's name softly, then more firmly. No response. He would touch their arm. Still no response. They were profoundly asleep, unrousable even by these stimuli. Yet their brain waves screamed awake. The next step was to link this physiological state to a mental experience. This was the bridge between Kleitman's world of physiology and the forbidden world of the mind. Aserinsky began waking subjects during these periods and immediately asking for a report of their mental content. The results were not always clear-cut, but a pattern emerged. Reports from awakenings during non-REM sleep, especially deep sleep, were often blank or consisted of vague, static thoughts. I was thinking about the sound of the machine. But reports from awakenings during the rapid eye movement periods were different. They were often narrative, visual, emotional. I was climbing a ladder that kept getting longer. I was arguing with my brother. The correlation wasn't 100%, but it was strong enough to be compelling. It suggested that this peculiar brain state was the likely substrate of dreaming. Armed with this data, Aserinsky finally approached Kleitman. The meeting was tense. Kleitman listened, examined the polygraph rolls, and expressed deep skepticism. His lifetime of work had mapped sleep as a gradual descent into quiescence. This active sleep contradicted that map. He worried about artifacts, about poor electrode contact, about the subject's state. But to his immense credit, Kleitman did not shut the inquiry down. He imposed rigor. He demanded more subjects, more controls, more meticulous documentation. He pushed Aserinsky to be a better scientist. In doing so, he ensured that when the discovery was finally announced, it would be bulletproof. And so, the nocturnal routine intensified. The laboratory became a stage for a quiet revolution. The subjects slept. The polygraph pen scratched. And two men, one young and anxious, the other old and cautious, watched the lines on the paper, trying to decipher a message from a kingdom they never knew existed, the kingdom of the sleeping, dreaming brain. The winter of 1952 to 1953 in Chicago was a season of quiet obsession within the walls of the physiology lab. Aserinsky, now consumed by the mystery of the rapid eye movements, expanded his pool of subjects. He recruited fellow students, friends, anyone willing to spend a night wired to the machine. Each subject was a new puzzle, a new confirmation. The pattern held. The 90-minute cycles, the awake-like EG, the bodily stillness, the unrousability. One subject, however, was unique. He was not a fellow student, but an 8-year-old boy, Armand, Aserinsky's own son. Using one's child as a research subject would raise ethical eyebrows today. But in the context of the time and the low-risk nature of the recordings, it was not unusual. For Aserinsky, it was also a matter of practicality and trust. He could ensure the electrodes were properly applied. He could monitor the night with the parent's attention, and perhaps unconsciously, he felt that this intimate exploration of sleep should include the most intimate of subjects. The nights with Armand in the lab added a poignant, human layer to the data. Here was the scientific method embodied in a family relationship. The father as objective observer, the son as the sleeping subject. Aserinsky would carefully attach the electrodes to his son's face, a delicate operation requiring patience. He would tell him to sleep well, then retreat to the monitoring room. He would watch as Armand's sleep deepened, his breathing evening out. Then, like clockwork, the pens would jump. His son's eyes, behind closed lids, would be darting back and forth, as if watching a frantic ping-pong match. His brain waves would shift to their wakeful pattern, and Armand would be dreaming. What did he dream of? Aserinsky would sometimes wake him gently during these periods, following the protocol. The reports were those of a child, dreams of playing, of school, sometimes of cartoon characters. The content was mundane, but its correlation with the physiological state was another brick in the wall of evidence. The laboratory was no longer just a place of wires and machines. It was a place where the private world of a child's imagination became a data point in a groundbreaking scientific theory. This period was also one of intense methodological refinement. Kleitman's skepticism was a forcing function. Aserinsky had to rule out every possible artifact. One major concern was that the eye movement signals were actually caused by tiny twitches of the facial muscles around the eyes, the orbicularis oculi, not by the movements of the eyeballs themselves. To test this, Aserinsky devised a simple but clever experiment. He placed a small, delicate piece of tissue paper over a subject's closed eye. If the eyeball itself was moving, it would disturb the paper. He then filmed the subject's face during a rapid eye movement period. The film, grainy and silent, showed it clearly. The tissue paper fluttered with each jerk of the pen on the polygraph. The eyes were indeed moving rapidly beneath the lids. It was a direct visual confirmation. The signal was real. Another concern was the EEG. Could the wake pattern be caused by the eye movements themselves, electrically bleeding into the brainwave leads? Aserinsky moved the EEG electrodes to different locations on the scalp, far from the eyes. The pattern persisted. The activated brain was a global phenomenon, not a local artifact. Piece by piece, the alternative explanations were dismantled. What remained was a robust, repeatable phenomenon, a distinct state of sleep characterized by 1. Rapid, conjugate eye movements, 2. A low voltage, fast EEG pattern resembling wakefulness, 3. Near total suppression of voluntary muscle tone, except for the eyes and the diaphragm, and 4. A high likelihood of vivid dream recall upon awakening. The time came to write it up. Aserinsky, under Kleitman's stern guidance, began drafting the paper. The writing process was itself an education. Kleitman insisted on a tone of dry, unemotional precision. No speculation. No grand claims about discovering dreams. Just the facts. The title they settled on was a masterpiece of understatement. Regularly occurring periods of eye motility and concomitant phenomena during sleep. The word dream appeared only once in the entire paper, and only in reference to the subjective reports upon awakening. This cautious approach was strategic. Kleitman knew that making claims about the biology of dreaming would invite immediate attack from the psychoanalytic establishment, which saw dreams as its exclusive domain. By sticking to the physiology, the eye movements, the EEG, the cycle, they were speaking a language other physiologists would understand and respect. They were building a beachhead. Let others make the connection to dreams explicit later. The paper was submitted to the journal Science. It was accepted. On September 4th, 1953, it was published. In the quiet, musty libraries of universities and research institutes around the world, a few alert readers stumbled upon it. For most, it was a minor curiosity, but for a handful, it was a lightning bolt. One of those struck by lightning was a young medical student at the University of Chicago named William Dement. Dement was working on a different project in Kleitman's lab, but he was instantly captivated by Aserinsky's findings. He saw the implications immediately. Here was a window, not just into sleep, but into the mind itself, a biological marker for a subjective experience. Dement would soon become the dynamic force that propelled REM sleep from a curious observation to a central pillar of neuroscience. For Aserinsky, the publication should have been a moment of triumph. It was the culmination of 2 years of painstaking work. It was his ticket to a PhD. Yet the atmosphere was mixed. The discovery was clearly significant, but credit was already subtly shifting. In the academic world, the senior author, Kleitman, often received the primary acknowledgement. Aserinsky was the junior author, the graduate student who did the work. It's a timeless academic story. He felt the sting of being seen as a pair of hands rather than the intellectual driving force. This resentment would simmer for decades. Nevertheless, the deed was done. The map of sleep had been redrawn. It was no longer a flat plane of unconsciousness, but a rolling landscape with the mysterious, active peak recurring every 90 minutes. The foundation for all modern sleep science, and for the understanding of your own sleep this very night, had been poured in that Chicago basement by a persistent student, a skeptical professor, and a little boy who dreamed while his father watched the pens dance. With the publication of the 1953 paper, the discovery left the intimate, uncertain space of the laboratory and entered the broader, often unforgiving, world of science. The initial reaction was not a chorus of acclaim, but a spectrum ranging from indifference to skepticism to keen interest. The physiological community absorbed the news quietly. Sleep research was a niche field, and a paper about our movements during sleep, even remarkable ones, was easy to overlook. The psychoanalytic community, for the most part, ignored it. Dreams were symbols, not brain states. This was physiology trespassing on psychology's sacred ground. But within Kleitman's own lab, the energy shifted. William Dement, the medical student who had been electrified by the finding, now threw himself into the new field with evangelical fervor. He became, in effect, the first true REM sleepologist. While Aserinsky, his degree secured, began to drift away from sleep research, a move fueled by both career pragmatism and his growing bitterness over credit, Dement saw a lifetime's work ahead. Dement's first major contribution was to ask a more pointed question than Aserinsky and Kleitman had dared in their cautious paper. Is REM sleep necessary? What happens if you don't get it? To answer this, he designed the selective REM deprivation experiment, a study that would become a classic of sleep science. The protocol was simple in concept but grueling in execution. Volunteers would come to the sleep lab for a series of consecutive nights. They were allowed to sleep normally, except for one brutal intervention. The moment the polygraph indicated the onset of REM sleep, a technician, often Dement himself, would enter the room and wake them. They would be kept awake for a few minutes, then allowed to fall back asleep, only to be awakened again at the next REM onset. They were thus deprived of REM sleep specifically, while still getting hours of non-REM sleep. The results were startling. After just a few nights of this, subjects began to show psychological changes: increased anxiety, irritability, difficulty concentrating, and increased appetite. More strikingly, their drive for REM sleep seemed to build up. When, after several deprivation nights, they were finally allowed to sleep uninterrupted, their brains rushed into REM sleep earlier, stayed in it longer, and the REM periods were more intense and frequent. This REM rebound effect was powerful evidence that REM sleep was not a passive byproduct of sleep, but a need. The brain actively regulated it, and if deprived, would work to reclaim it. This was a paradigm shift. Sleep was not just a single, homogeneous state of rest. It contained within it a specific, vital component with its own separate regulatory mechanisms. While Dement was exploring the necessity of REM, other researchers began dissecting its mechanisms. In France, the neurobiologist Michel Jouvet was conducting his own pioneering work, primarily on cats. Jouvet made a series of critical discoveries. He confirmed that the rapid eye movements were indeed conjugate, both eyes moving together in the same direction. More importantly, he discovered that during this state, which he famously dubbed paradoxical sleep, somnoparadoxal, the major muscle groups of the body were effectively paralyzed. He identified the brainstem region responsible for this paralysis, a group of neurons that sent inhibitory signals down the spinal cord, preventing motor neurons from firing. This explained why we don't act out our dreams. It was a safety mechanism, isolating the brain's intense activity from the sleeping body. Jouvet's work added crucial pieces to the puzzle. REM sleep was now defined by a triad. 1. Cortical activation, the awake-like EEG. 2. Rapid eye movements. And 3. Muscle atonia, paralysis. He also showed that this state was phylogenetically ancient, present in all mammals and even in birds. Dreaming, or at least the REM state, was not a luxury of human consciousness. It was a fundamental feature of the mammalian brain. Back in the United States, the architectural map of a full night's sleep was being meticulously drawn. Researchers, using all-night EEG recordings, began to describe the predictable cycle, the descent from wakefulness through Stage 1 light sleep. Stage 2, characterized by sleep spindles and K-complexes, into the deep, slow-wave sleep of Stages 3 and 4, now often called N3. After about 70 to 90 minutes, the brain would ascend back through the lighter stages, but instead of waking, it would enter the first REM period of the night. This cycle would repeat 4 to 5 times. Crucially, they noted that the composition of the cycles changed as the night progressed. Deep slow-wave sleep dominated the early cycles, while REM sleep periods became longer and more intense in the later cycles, just before morning awakening. This explained why people often wake from a dream, and why morning dreams feel particularly long and vivid. The discovery of this architecture had practical implications. It changed how sleep disorders were understood. The terrifying experience of sleep paralysis, waking up unable to move, sometimes with the hallucinated sense of an ominous presence in the room, was now clearly seen as a dissociation of REM components. The person regains consciousness while the muscle atonia of REM sleep is still active. The frightening hallucination is likely a dream fragment intruding into waking perception. Similarly, REM sleep behavior disorder, where people physically act out their dreams, was understood as a failure of that protective muscle paralysis. By the late 1950s, a new scientific discipline was coalescing. Sleep laboratories began to sprout up at major universities. Conferences were organized. The Association for the Psychophysiological Study of Sleep, APSS, the forerunner of today's professional sleep societies, was founded. REM sleep was the catalyst. It provided the hard, objective, measurable core that made the study of sleep, and by extension, dreaming, respectable scientific pursuit. Yet, amid this institutional progress, a personal story was fading. Eugene Asarensky, having earned his Ph.D., left the University of Chicago. He took a series of research positions, none of which focused on sleep. He felt sidelined. The narrative that solidified in the scientific community was often Kleitman and his colleagues discovered REM sleep. Dement's energetic advocacy further shaped the story. Asarensky, the quiet, meticulous observer who first noticed the dancing pens and had the tenacity to pursue their meaning, felt written out of his own discovery. It was a wound that would never fully heal, a reminder that science is a human endeavor, with all the accompanying frailties of ego, credit, and memory. But the discovery itself was now bigger than any one person. It had taken on a life of its own. From a curious squiggle on a polygraph roll in a Chicago basement, it had grown into a fundamental principle of brain function. It revealed that our brains are not passive at night, but engaged in a scheduled, active, and essential process. We now knew that every night we leave our waking selves behind and enter a cyclical landscape where we periodically visit a strange, active province, a province of paralyzed bodies, awake brains, darting eyes, and vivid, private stories. As the 1950s drew to a close, the Chicago laboratory's specific story began to blend into the broader narrative of a scientific revolution. The discovery was no longer just Asarensky and Kleitman's curious observation. It was the foundation of a new understanding of the brain, sleep, and the mind. This final part of our chapter reflects on the legacy of that small lab, the human dimensions often lost in the textbook summaries, and how this history resonates in the quiet of your own night. For Nathaniel Kleitman, The REM discovery was the crowning achievement of a long, meticulous career. It validated his lifelong belief that sleep was a legitimate and rich subject for physiological inquiry. He continued to research and teach, becoming known as the father of modern sleep research. He lived to be 104 years old, a testament perhaps to the benefits of good sleep, or simply to formidable genetics. In his later years, he saw the field he helped create blossom into a major medical and scientific discipline. He remained proud, if characteristically understated, about his role. For Eugene Aserinsky, the path was more difficult. He felt the discovery had not brought him the recognition or career trajectory he deserved. He moved through several academic and government posts, his work often tangential to sleep. A sense of disappointment followed him. It was only decades later, as historians of science and figures like William Dement began to meticulously document the origins of the field, that Aserinsky's crucial role as the primary discoverer was more widely acknowledged. In the 1990s, he began to receive invitations to speak at conferences as a pioneer, a form of bittersweet vindication. He died in 1998, knowing his place in history was finally being secured, though the delay had cost him dearly in personal and professional satisfaction. William Dement, of course, became the tireless propagandist and builder of the field. He founded the first dedicated sleep disorders clinic at Stanford, trained generations of sleep researchers and physicians, and authored the seminal textbook Principles and Practice of Sleep Medicine. He was instrumental in establishing sleep medicine as a board-certified medical specialty. For Dement, the Chicago discovery was the spark that ignited a lifelong mission to conquer what he called the last great frontier of medicine. His enthusiasm was infectious, and he did more than anyone to move sleep science from the basement to the mainstream. And what of Armin, the boy who slept for science? He grew up, pursued his own life, largely away from the spotlight of his father's early work. But in a profound sense, he represents every one of us. He was an innocent participant in the mapping of a universal human experience. His childhood dreams, reported to his father in the dim light of the lab, became part of the data that proved a dream is not just a story, but a state. The legacy of the Chicago laboratory is not merely a set of facts, the 90-minute cycle, the activated EEG, the rapid eye movements. Its deeper legacy is a shift in perspective. It moved dreaming from the realm of the supernatural and the psychoanalytic couch into the realm of biology. It allowed us to see sleep not as a void, but as a structured, dynamic, and essential process. It gave us the concept of sleep architecture, a blueprint for the night that is as unique to each individual as a fingerprint, yet follows universal rules. This shift has profound personal implications. Knowing about REM sleep changes how we think about our own nights. That groggy feeling after being wrenched from deep sleep? That's sleep inertia. The vivid dream you remember just before the alarm? That was a long, late morning REM period. the sensation of falling as you drift off, a hypnotic jerk from stage one sleep. The discovery provided a language for experiences that were previously ineffable. It also changed our approach to health. The understanding of REM's necessity led to the recognition of sleep deprivation as a serious public health issue. It helped explain the effects of medications, alcohol, and depression on sleep patterns. It created the entire field of sleep medicine, which now treats millions for insomnia, sleep apnea, narcolepsy, and restless leg syndrome. The simple act of monitoring a night's sleep in a clinic, the polysomnogram, is the direct technological descendant of Aserinsky's polygraph and his all-night vigils. As we close this chapter on the Chicago lab, let us bring the story home. To you, right now, you are not in a laboratory. You are in your own personal sleep chamber. But the principles discovered in that lab are at work within you at this very moment. Your brainstem is preparing to modulate your muscle tone. Your pons is getting ready to send chaotic signals to your visual cortex. Your amygdala may be primed to color the coming dream with emotion. You are walking, breathing testament to the reality they discovered. So tonight, as you feel sleep approaching, think of it not as a surrender to oblivion, but as an embarkation on a scheduled voyage. The first cycle will begin soon after you close your eyes. You will sail into the calm, deep waters of slow-wave sleep. Then, you will ascend to the strange, active shores of REM. You may not remember the journey, but it will happen. It happens to kings and beggars, to scientists and infants, to you and to me. Let this knowledge be a source of deep comfort and connection. You are participating in a biological ritual that is both utterly personal and utterly universal. The same process that Eugene Aserinsky saw as squiggles on a page is unfolding in your head right now. You are living the discovery. Now let the history fade. Let the names and dates soften. What remains is the phenomenon itself, the beautiful, complex, essential rhythm of the sleeping brain. Your brain, trust it. It knows what to do. It has been following this script for eons, long before there were laboratories to uncover its secrets. Surrender to the cycle. There is nothing more you need to know tonight. The explorers have mapped the territory. Now it is your turn to travel. The discovery that the sleeping brain periodically erupts into a state of wakeful activity was, as we've seen, met with a mixture of skepticism and fascination. But for the scientists of the late 1950s and 1960s, the initial what quickly gave way to a more urgent how and why. How does the brain flip into this paradoxical state? What machinery triggers the rapid eye movements, the muscle paralysis, the cortical activation? Why would evolution bother with such a complex, risky-seeming process? This chapter is the story of moving from observation to mechanism, from watching the pens dance on the polygraph to understanding the ghost in the machine. The first major battlefield in this new war of understanding was the brainstem. This ancient part of the brain, sitting atop the spinal cord, is the control center for life's basic rhythms: breathing, heart rate, arousal. Early lesion studies in cats, a mainstay of mid-century neuroscience, provided crucial clues. Researchers like the Italian neurologist Giuseppe Maruzzi and the American Horace Magown had already shown that stimulating the brainstem's reticular formation could jolt an animal from sleep to alert wakefulness. It was the brain's on switch. Now scientists began making precise, surgical lesions in the brainstems of cats. They discovered something astonishing. If you made a cut between the pons, the upper part of the brainstem, and the midbrain, you could isolate the forebrain, the seat of consciousness and complex thought, from the lower brainstem. In this isolated brain preparation, the cat's forebrain fell into a permanent state of slow-wave sleep. It was as if the on switch had been disconnected. But more revealing was the opposite experiment. If you made a cut lower down, between the medulla and the spinal cord, encephally isole, the animal's forebrain continued to cycle between sleep and wakefulness. This showed that the basic sleep-wake rhythm generator lived in the brainstem, above the medulla. The French neurobiologist Michel Jouvet, working in Lyon, took this further. He began making even more precise lesions within the pons, and he found a specific area that, when damaged, caused a bizarre and dramatic effect. Cats would lose the muscle paralysis of REM sleep. They would enter the REM state. Their EEG would show the characteristic activation. Their eyes would dart, but their bodies would not be still. They would stand up, pace, pounce at invisible prey, and even exhibit defensive or attack behaviors, all while technically asleep and unconscious. Jouvet had discovered the neurons responsible for triggering the muscle autonomia of REM sleep. He called this region the pontine tegmentum. This was a landmark finding. It localized a key component of the REM state to a specific patch of neurons. It also explained the condition we now call REM sleep behavior disorder, RBD, where humans act out their dreams, a failure of this very brainstem system. Jouvet's lesion cats were, in effect, the first animal models of RBD. While Jouvet was mapping the paralysis switch, other researchers were hunting for the activation switch. What was turning the cortex back on during REM? The answer, again, lay in the brainstem. A collection of neurons, primarily using the neurotransmitter acetylcholine, was found to become highly active at the onset of REM sleep. These REM-on cells, located in the pons, would fire in bursts, sending signals racing upward. One pathway went to the thalamus, the brain's grand central station for sensory information. During wakefulness, the thalamus relays sights, sounds, and touches to the cortex. During REM sleep, these acetylcholine signals essentially jumpstart the thalamus, causing it to generate its own internal activity, which it then broadcasts to the cortex. This internal broadcast, not external reality, becomes the raw material for our dream imagery. Another pathway from the REM-on cells projects to the basal forebrain and directly to the cortex. further driving the activated, fast EEG pattern. So, the brainstem isn't just allowing the cortex to wake up, it's actively forcing it into an awake-like state, using a shower of acetylcholine. But the brain is a system of checks and balances. For every on switch, there is an off switch. Researchers soon identified REM off cells. These neurons, using neurotransmitters like norepinephrine and serotonin, the very chemicals targeted by many antidepressants, are the stalwarts of wakefulness. They fire steadily while we are awake, helping to maintain focus and alertness. As we fall asleep, their firing slows, and when the REM-on cholinergic cells fire up to initiate a REM period, these REM-off cells fall almost completely silent. This reciprocal interaction, cholinergic cells firing, monoaminergic cells shutting down, is the fundamental clockwork of the REM and REM cycle. This elegant push-pull mechanism in the brainstem explained the how of REM's basic physiology. But it raised another question. What about the rapid eye movements themselves? Why do the eyes dance? One theory, still largely held today, is that they are related to the visual imagery of dreams. The pons send signals to the muscles controlling eye movement, just as it would if you were actually looking around at a scene in the waking world. In a sense, your eyes are following the action of your dream. This is supported by studies showing that the direction of eye movements sometimes correlates with the reported direction of gaze in the dream. Yet, the eyes also move in people blind from birth, who do not have visual dream imagery. This suggests the eye movements are fundamental, hardwired output of the REM state generator, perhaps a vestigial scanning reflex or part of a more basic process of neural activation, not always tied to a specific dream picture. As the 1960s progressed, the model grew more sophisticated. REM sleep was no longer just a curious, active state. It was a highly regulated brain mode, orchestrated by a precise dialogue of neurotransmitters in the brainstem, with dramatic downstream effects on the thalamus, cortex, and motor systems. It was a paradox because it mixed elements of wakefulness, cortical activation, with elements deeper than sleep, muscle paralysis, unresponsiveness. Juvet's term, paradoxical sleep, captured this essence perfectly, and is still the preferred term in much of the world. For the scientists involved, this period was one of exhilarating puzzle solving. They were reverse engineering a piece of biological firmware, line by line. Each experiment, a lesion here, a chemical injection there, revealed another cog in the machine. They were proving that even our most mysterious, personal experiences are built from tangible, physical parts. As you listen, consider this. The very sensations of drowsiness you may be feeling now are the result of REM-off, monoamine neurons beginning to slow their firing. The transition into your first REM period later tonight will be triggered by a specific cluster of cells in your pons switching on, flooding your brain with acetylcholine, while simultaneously ordering your spinal cord to lock your body in place. The dream you may have will be the result of your thalamus and cortex, driven by that brainstem pulse, weaving a story from memories and emotions. You are not just a dreamer. You are the audience in a theater run by an ancient, automatic stage crew deep in your brainstem. The discovery of REM sleep was the moment we first met that crew. While brainstem researchers were deciphering the machinery of REM sleep, a parallel revolution was taking place in our understanding of its function. If this complex state was so tightly regulated and evolutionarily conserved, it must serve a vital purpose. But what? The question, why do we dream, had been asked by philosophers for millennia. Now, for the first time, scientists could reframe it in concrete, biological terms. What is the function of REM sleep? The first major theory to emerge from the new science was the activation synthesis hypothesis, proposed by psychiatrist J. Allen Hobson and neurophysiologist Robert McCarley in 1977. It was a bold, mechanistic, and deliberately anti-Freudian shot across the bow. Hobson and McCarley started with the facts of REM neurophysiology, the random, chaotic firing of the pons activation. This noisy signal, they argued, is sent up to the higher brain regions responsible for perception, memory, and emotion. The forebrain, ever the meaning-making machine, receives this random internal signal and does its best to synthesize a coherent narrative from it. It pulls in bits of recent memory, emotional concerns, and sensory fragments to create a story, a dream. In this view, dreams are essentially the brain's attempt to make sense of neurological noise. The bizarreness of dreams, the sudden scene shifts, the impossible physics, the odd characters, is a direct result of the brain trying to impose order on a fundamentally random signal. The theory was elegant and grounded in the new neurobiology. It demystified dreams, stripping them of Freudian latent content and wish fulfillment. Dreams were not cryptic messages from the unconscious. They were cognitive babbling, a byproduct of a brain cleaning its circuits. The activation synthesis model was hugely influential and remains a cornerstone, but it also had critics. It seemed to reduce the rich, often emotionally resonant tapestry of dreams to mere epiphenomena, interesting side effects with no real function of their own. If dreams were just noise, why would the brain have such an elaborate, energy-intensive system to produce them? Wouldn't evolution have selected against it? This led to the rise of functional theories. Perhaps REM sleep itself had a purpose, and dreams were just the conscious tip of that functional iceberg. Several compelling hypotheses emerged, each supported by different lines of evidence. Memory processing and consolidation. This became, and remains, one of the strongest candidates. Researchers like Carlisle Smith and Robert Stiggold began designing experiments. They would teach subjects a new skill, like a finger-tapping sequence or a complex visual puzzle, and then either let them sleep normally, deprive them of REM sleep, or deprive them of slow-wave sleep. The results were striking. REM sleep, particularly later in the night, seemed crucial for consolidating procedural memory, the how-to memory, and for emotional memory processing. Slow-wave sleep, in contrast, was more important for declarative memory, facts, and events. The theory suggests that during REM, the brain replays and strengthens important neural connections formed during the day, integrating new learning with old knowledge and stripping away the intense emotional charge from traumatic or significant events. The dream narrative might be a shadow of this massive, behind-the-scenes data transfer. Brain development and neuroplasticity. REM sleep is extraordinarily abundant in infants. Newborns spend about 50% of their sleep in REM, compared to about 20 to 25% in healthy adults. This led scientists like Howard Rothward to propose the ontogenetic hypothesis. They suggested that the endogenous activation of the brain during REM sleep in the fetus and infant is crucial for proper brain development. It helps wire up the visual system before there's much to see, mature the motor pathways while the body is immobilized, and establish basic neural networks. In this view, REM sleep is the brain's way of self-stimulating and exercising its circuits during critical periods of growth. The high amount of REM in early life is less about dreaming in a narrative sense and more about fundamental biological programming. Emotional regulation. The strong involvement of limbic system structures, like the amygdala, the brain's fear and emotion center, during REM sleep is well documented. The amygdala is highly active, while the prefrontal cortex, the rational, inhibitory CEO of the brain, is relatively quiet. This neurochemical environment, high emotion, low logic, is the perfect theater for processing emotional experiences from the day. The theory posits that REM sleep allows us to rehearse emotional scenarios in a safe, offline environment, stripping away the raw visceral intensity while preserving the memory's content. It's a form of overnight therapy. Bad dreams or nightmares might be a sign of this process, working through particularly difficult material. Physiological restoration for the brain, while slow-wave sleep seems to be for bodily repair, releasing growth hormone, repairing tissues. REM sleep may be for brain-specific restoration. The high metabolic rate of the awake brain produces waste products. The glymphatic system, the brain's waste clearance system, is most active during sleep. Some theories suggest the unique physiological state of REM, with its changes in blood flow and possibly in cerebrospinal fluid dynamics, might facilitate this cleaning process for specific neural tissues. By the 1980s, the field had moved from a single, grand theory to a more nuanced view. REM sleep is multifunctional. It likely serves several purposes that have evolved over time. Its primary role may be different in an infant brain development than in an adult memory and emotional processing. The vivid dreams we experience are likely just one visible manifestation of this deep, multifaceted neural work. This period also saw the tools of inquiry grow more sophisticated. Beyond lesions and polygraphs, scientists now had positron emission tomography, PET, and later functional magnetic resonance imaging fMRI, to watch the living human brain during REM sleep. They could see the hot and cold spots, the hyperactive limbic system, the active visual and motor cortices, despite the body's paralysis, and the deactivated dorsolateral prefrontal cortex, explaining the loss of self-reflection and critical thinking in dreams. The dream, once the province of priests and poets, was now a legitimate subject for the most advanced tools of neuroscience. The question had shifted from "do dreams have meaning?" to "what work is the brain doing that gives rise to the experience of meaning?" The march of science rarely proceeds in a straight line. As the neurobiological and functional understanding of REM sleep solidified in the late 20th century, it also began to reveal profound and sometimes unsettling connections to the realm of mental health, neurology, and even creativity. The discovery of REM was no longer just about explaining a normal night's sleep. It was becoming a key to diagnosing and understanding a host of human conditions where the boundaries of consciousness, memory, and self blur. One of the most direct links was with mood disorders. The connection between sleep and depression had long been observed, but now it had a physiological signature. Individuals with major depression were found to have striking REM sleep abnormalities. They often entered their first REM period much faster after sleep onset, a phenomenon called shortened REM latency. Their REM periods were longer and more intense in the first half of the night, and their eyes moved more vigorously. It was as if the REM pressure system was dysregulated, bursting forth too soon and too strongly. This observation wasn't just a correlation, it informed treatment. Many of the most effective early antidepressant medications, the tricyclics and monoamine oxidase inhibitors, MAOIs, were found to powerfully suppress REM sleep. This was consistent with their mechanism of action. They boosted the levels of the very REM-off neurotransmitters, norepinephrine and serotonin, that normally keep the cholinergic REM-on cells in check. For some psychiatrists, the therapeutic effect of these drugs seemed intrinsically linked to their REM-suppressing properties. It led to the bold, if controversial, REM deprivation hypothesis of antidepressant action. Perhaps, the theory went, depression is maintained by a dysfunctional REM process, and interrupting that process, even chemically, allows the brain to reset. While this view is now considered too simplistic, newer antidepressants like SSRIs have more complex effects on sleep architecture. The link remains fundamental. Sleep disturbances, especially REM disturbances, are a core diagnostic feature of depression and a harbinger of relapse. Studying REM became a window into the neurochemical turmoil of the depressed brain. Beyond mood, REM sleep was implicated in the very architecture of learning and psychosis. The neurochemical profile of REM, high acetylcholine, low serotonin, and norepinephrine, resembles, in some ways, the brain state of hallucinations and certain aspects of schizophrenia. This led to theories proposing that REM sleep might be a biological model for psychosis, a state where internally generated perceptions override external reality. The fact that we all willingly enter this psychotic state every night, and usually emerge unscathed, is a testament to the protective boundaries the brain erects between sleep and waking. When those boundaries break down, as in conditions like schizophrenia or under the influence of certain drugs, the dreamlike quality of REM can intrude into wakefulness. On the other end of the spectrum, REM sleep was linked to creativity and problem-solving. The old tales of scientists and artists finding inspiration in dreams gained a biological basis. The loose, associative connections forged during REM, the integration of disparate memories, and the quieting of the critical prefrontal cortex could create a fertile ground for novel insights. The famous examples are legion. Dmitri Mendeleev envisioning the periodic table in a dream, Paul McCartney hearing the melody for Yesterday in a dream, Otto Lowy designing the Nobel-winning experiment that proved chemical neurotransmission after a dream gave him the idea. REM sleep, it seemed, wasn't just consolidating memory. It was recombining it in novel ways. This creative function was further supported by studies on sleep-dependent memory consolidation. Researchers found that people who slept after learning a task, particularly if they experienced REM sleep, not only remembered it better, but were also more likely to exhibit insight, to grasp hidden rules or solutions that weren't apparent during initial learning. The brain wasn't just replaying the day. It was editing it, finding patterns, and making intuitive leaps. Meanwhile, the clinical world of sleep medicine was being built directly upon the foundation of REM discovery. The polysomnogram, PSG, the all-night sleep study, became the gold standard for diagnosis. It monitored not just EEG, EOG, eye movements, and EMG, muscle tone, but also heart rhythm, breathing, and oxygen levels. This allowed for the precise diagnosis of disorders that specifically targeted REM sleep. Narcolepsy, this disabling condition, characterized by sudden sleep attacks, and cataplexy, sudden loss of muscle tone triggered by emotion, was understood as a profound dysregulation of REM sleep boundaries. In narcolepsy, the paralysis and dream imagery of REM can intrude directly into wakefulness, sleep paralysis, hypnagogic hallucinations, and the switch controlling muscle autonomia can be triggered by strong emotions, cataplexy. Narcolepsy became the paradigmatic REM sleep disorder. REM sleep behavior disorder, RBD, as predicted by Juvit's lesioned cats. This condition, where patients physically act out violent, vivid dreams, was confirmed as a failure of the brainstem systems that induce muscle autonomia during REM. Importantly, RBD was found to be a powerful early predictor of neurodegenerative diseases like Parkinson's disease and Lewy body dementia, often appearing years or even decades before other symptoms. This made REM sleep monitoring a potential crystal ball for neurology. By the turn of the 21st century, REM sleep had transcended its origins. It was no longer just a curious stage of sleep. It was a core brain state with deep ties to our mental health, our cognitive abilities, our neurological resilience, and our creative spark. It was a biological rhythm as fundamental as the circadian cycle, a separate consciousness that visited us nightly. The impossible state that Aserinsky had stumbled upon was now seen as a vital and vulnerable pillar of human biology. Tinkering with it through drugs, disease, or deprivation had profound consequences. Protecting it became synonymous with protecting mental and neurological health. We have traveled from the electrical squiggles on a polygraph roll to the intricate dance of neurotransmitters in the brainstem, from philosophical speculation to the clinical realities of sleep medicine. We have seen REM sleep evolve in the scientific mind from an anomaly to a mechanism, and from a mechanism to a multifaceted pillar of human biology. As we conclude this chapter on the birth of REM as a scientific concept, we arrive at a place of synthesis and wonder. We now stand at the threshold of the most important laboratory of all, the one inside your own skull tonight. The story of REM sleep is, ultimately, a story about integration. It integrates the biological and the psychological. It ties the random firing of pontine neurons to the epic narratives of our dreams, the evolutionary and the personal. It links a conserved mammalian brain state to our most private fears, desires, and creative leaps. Health and disease. It shows how a delicate neural balance, when disrupted, can herald depression, neurodegeneration, or unleash creative genius. This integrated view offers us a new way to relate to our own nights. We are not merely getting rest. We are undergoing a structured, cyclical process of neural maintenance, emotional digestion, and cognitive reorganization. The REM period is the phase where the brain, liberated from the constraints of external reality and logical oversight, does its deepest, most associative work. So, what does this mean for you, the listener, seeking relaxation or sleep? It means you can reframe the very act of closing your eyes. You are not running from the day. You are initiating a vital, internal processing session. The worries of the day, the skills you practiced, the emotions you felt, all of them are queued up for overnight handling. The first shift is deep, slow-wave sleep, filing away facts and physically restoring the body. The second shift is REM sleep, where the emotional tone is adjusted, skills are cemented, and new connections are woven. This knowledge can be a powerful antidote to sleep anxiety. Lying awake, frustrated that sleep won't come, often stems from a desire to control the process. Understanding REM sleep invites a healthy surrender. You don't need to make your brain dream or consolidate memories. You simply need to provide the conditions, darkness, quiet, time, and the ancient, automated machinery will engage. The 90-minute cycle is a resilient, self-regulating program. Trust it. Furthermore, appreciating the purpose of REM can change how we view our dreams. Instead of searching for literal interpretations or feeling disturbed by their strangeness, we can see them as symptoms of health. The bizarre narrative is a sign that the synthesis engine is running. The intense emotion in a dream is evidence of the amygdala doing its overnight therapy. Even nightmare, while distressing, can be viewed as the brain working through a particularly difficult piece of emotional data, perhaps with the volume turned up too high. As the science has matured, a beautiful humility has emerged. We have not solved dreaming. We have not reduced the surreal poetry of a dream to a mere equation. Instead, we have discovered the stage upon which that poetry is performed. We know about the lighting grid, the ascending arousal system, the special effects, the Pontine generator, and the safety mechanisms, the muscle atonia. We know the playwright is a collaboration between memory, emotion, and random neural noise. But the play itself, the specific story that unfolds for you tonight, remains a unique, unpredictable, and personal creation. Science has illuminated the theater, but the performance is still yours alone. This brings us to the present moment. You are listening, perhaps in a dim room, your body growing heavy. The biological precursors to your first REM period are already gathering. Levels of serotonin and norepinephrine are beginning their gradual decline. Soon, a cluster of cholinergic cells in your pons will reach their threshold and fire. A command will be sent down your spinal cord, gently locking your voluntary muscles in place. A barrage of signals will hit your thalamus, switching it from a relay of the outer world to a broadcaster of an inner one. Your visual cortex will light up with internally generated imagery. Your amygdala will infuse it with feeling, and your prefrontal cortex, the critic, will take a step back. You will enter the paradox. You will be gone, yet present, paralyzed, yet flying. The audience and the actor. This is not a flaw or a bug in human design. It is, according to decades of rigorous science, a feature. A necessary, beautiful, and complex feature. Let this understanding be the final layer of relaxation. There's nothing you need to do, no effort to make. The most sophisticated, personalized restoration protocol in the known universe is about to execute its code. Your only task is to not interfere. So, as we end this chapter on the science of REM's birth, let the science itself dissolve into experience. Let the words fade. Let the concepts of pons, amygdala, and acetylcholine soften into mere sensations. The feeling of eyelids growing heavy, the sound of your own breath deepening, the gentle release of the body into the support of the bed. You are not just going to sleep. You are embarking on a journey through a meticulously mapped, yet endlessly surprising, inner landscape. You will visit the land of deep, quiet waves, and you will visit the vibrant, chaotic, creative land of paradox. Both are essential. Both are you. Surrender to the cycle. It is older than you, wiser than your waking worries, and utterly dedicated to your well-being. The discovery is complete. Now experience it. The publication of Aserinsky and Kleitman's 1953 paper in Science did not immediately ignite the world. As we've seen, its initial reception was more of a slow burn than a wildfire. But within a few years, as more researchers, most notably William Dement, began to replicate, extend, and champion the findings, the scientific community could no longer ignore the implications. A shockwave began to spread, first through physiology and psychology departments, and then rippling out into psychiatry, neurology, and the broader culture. This chapter is about that shockwave, the collision of a new biological paradigm with established dogmas, the birth of dream research as a laboratory science, and the profound questions it forced humanity to ask about the nature of consciousness itself. The first front in this intellectual upheaval was the collision with Freudian psychoanalysis. For over half a century, since the publication of The Interpretation of Dreams in 1899, Sigmund Freud's theories had dominated the scientific understanding of dreams. In the Freudian view, dreams were the royal road to the unconscious. They were carefully crafted psychic artifacts, born of repression and wish fulfillment. Their bizarre content, the manifest content, a censored code that could be deciphered by a trained analyst to reveal the hidden, instinctual, latent content. Dreaming was a purely psychological process, rooted in conflict and desire. The brain's physiology was irrelevant. The discovery of REM sleep delivered a direct challenge to this orthodoxy. Here was evidence that dreaming was tightly coupled to a specific, measurable, and cyclic biological state. It wasn't a sporadic psychic event. It was a scheduled physiological one. The dream reports that emerged from REM awakenings weren't cryptic puzzles to be solved through free association. They were data points correlated with eye movements and brain waves. For the new breed of physiologically minded researchers, Freud's complex symbolic interpretations seemed like unnecessary mystification. Why posit elaborate psychological censorship when a simple brainstem oscillator could explain the timing and perhaps even the bizarreness of dreams? Proponents of the new biology, like Harvard's J. Allen Hobson, launched direct attacks. Hobson's activation synthesis hypothesis was, in part, a deliberate provocation to the Freudian establishment. It argued that dreams were not meaningful narratives from the unconscious, but the brain's best effort to make sense of random neural noise from the pons. The meaning of a dream was an after-the-fact construction, not a hidden truth. This was heresy to the analysts. The resulting debate was fierce, often acrimonious. Traditional psychoanalysts dismissed the physiologists as reductionists, missing the forest of meaning for the trees of brain cells. The physiologists accused the analysts of building castles in the air without a foundation of empirical evidence. It was a classic clash of two cultures. The hermeneutic, interpretive world of the humanities-influenced psychology versus the hard, measurement-driven world of emerging neuroscience. But from this clash, something new and more robust began to emerge. A third way was pioneered by researchers who respected the biological data but refused to discard the psychological richness of dreams. Figures like Rosalind Cartwright at the University of Illinois and David Fowlkes, a cognitive psychologist, began conducting rigorous laboratory studies on dream content. They used the new tool of REM awakenings to collect thousands of dream reports from ordinary people, not neurotic patients on a couch. They analyzed these reports with systematic content analysis, looking for patterns, emotions, and continuity with waking life. What they found challenged both extremes. Dreams were not the meaningless neurological static of activation synthesis, nor were they the universally symbolic, conflict-driven dramas of Freud. Instead, they were often prosaic, emotionally charged continuations of daytime concerns. People dreamed about their work, their relationships, their worries. The day residue was a powerful factor. The bizarre elements were there, but they were embedded in a recognizable emotional and thematic context. Cartwright's work, in particular, suggested dreams played a role in mood regulation, helping people work through emotional problems overnight. This new, empirical dream science created a middle ground. It accepted the biological substrate, REM sleep, as the prime time for dreaming, but used controlled methods to explore the psychological content that this biological state produced. The dream was no longer a royal road to the infantile unconscious, but it was a window into ongoing cognitive and emotional processes. It was a form of thinking, different from waking thought, but thinking nonetheless. This shift had a democratizing effect. Dreaming was no longer the exclusive domain of the neurotic or the analyzed. It was a universal human experience that could be studied in the average college student sleeping in a lab. The dream lab became a new kind of scientific space, part hospital, part psychology experiment, part fortress of solitude for the sleeping mind. As the 1960s progressed, the tools grew sharper. The polygraph was joined by EEG spectral analysis, allowing for more nuanced reading of brain states. Researchers began studying not just when people dreamed, but what happened when they were deprived of it, dementia work, or when the REM state was manipulated with drugs. They explored dreaming in different populations: children, the elderly, people with brain injuries, even in other species. The shock of the initial discovery was giving way to the steady, cumulative work of building a new science. And this new science was starting to ask questions that reached far beyond sleep. If a specific brain state produced conscious experience, however bizarre, what did that say about the neural correlates of consciousness? REM sleep became a natural experiment. Here's a brain that is offline to the world, yet generating a world of its own. Studying it was a way to study the very ingredients of subjective experience: perception, emotion, memory, selfhood, and isolation. The dream, once a sideshow, was moving to center stage in the greatest mystery of all. How does the physical brain create the lived mind? The establishment of the Dream Laboratory as a legitimate scientific space catalyzed a golden age of discovery in the 1960s and 70s. Freed from the need to defend their basic premise, that dreams were physically locatable events, researchers could now ask refined, sometimes wild questions. This period was characterized by a spirit of systematic exploration, turning the mysterious continent of sleep into a mapped territory with distinct regions, laws, and even anomalies. One of the first major projects was normative studies. What does a typical dream look like? Under the leadership of psychologists like Calvin Hall and Robert Van de Castle, researchers began compiling and analyzing massive databases of dream reports collected from hundreds of ordinary people in sleep labs and through home dream diaries. Using content analysis, they coded dreams for characters, settings, social interactions, emotions, and objects. The results painted a picture that was both mundane and fascinating. Contrary to Freudian emphasis on sexuality and aggression, the most common emotions in dreams were apprehension, fear, and anxiety. Positive emotions were rarer. Dreams were often social. Most involve interactions with several other people. The dreamer was rarely alone in a void. Settings were often familiar, but frequently incongruous, e.g., one's childhood home combined with a workplace. Perhaps most surprisingly, a significant percentage of dreams, over a third in some studies, involved misfortune, being chased, attacked, failing a task, or experiencing loss. The typical dream was not a wish-fulfillment fantasy, but a somewhat stressful, socially complex simulation of daily life concerns. This normative work provided a crucial baseline, a dream atlas against which deviations in clinical populations, for example, could be measured. Alongside cataloging content, researchers probed the sources of dream imagery. The concept of day residue was validated and explored. Elements from the previous day, especially those that were emotionally salient or unfinished, frequently appeared in that night's dreams. But the incorporation was not literal. It was transformed, blended with older memories. This led to the study of dream incorporation, where researchers would expose subjects to specific stimuli, violent films, learning tasks, strong smells, before sleep, and see how they were transmuted in REM reports. Often, the emotional tone of the stimulus would persist, while the specific imagery would be altered or symbolic. A particularly elegant line of inquiry involved sensory incorporation during sleep. Researchers would spray a fine mist of water on a sleeper's face, or play a recorded tone, or flash a light during REM sleep, then immediately wake the subject. The external stimulus was often woven directly into the ongoing dream narrative. The mist became rain in a dream. The tone became a ringing phone. The light became a lightning flash or an exploding bomb. This proved that the dreaming brain was not completely isolated. It monitored the external world at a low level and could integrate sensory information, but it did so through its own, internally driven narrative filter. The Dream Lab also became a crucible for studying creativity and problem-solving. Building on anecdotal tales of dream-inspired discoveries, Researchers like Morton Schatzman conducted experiments. He would give subjects complex, visuospatial puzzles before bed. Some who slept and entered REM sleep would report dreaming about the puzzle, and upon waking, were more likely to have sudden insights or moments solving it. The loose, associative thinking of REM, unconstrained by linear logic, seemed to facilitate making novel connections that the focused, waking mind might miss. Perhaps the most philosophically provocative research of this era explored the nature of consciousness within the dream. How aware is the dreamer? What happens to the sense of self, of time, of logic? Through thousands of awakenings and interviews, a portrait emerged. The dreaming consciousness is characterized by reduced critical reflection. The dreamer rarely questions the bizarre events. The fact that a deceased relative is alive, or that one can fly, is accepted without surprise. Emotional dominance. Emotions are often intense and uncritically experienced, driving the narrative. Plasticity of identity. The dreamer's own identity can be fluid, observing the scene, participating in it, or even inhabiting another character. Distorted time. The sense of time is elastic, long, complex narratives can feel like they unfold over hours, but are estimated to occur in real time, with the REM period duration. This led researchers like Stephen LaBerge at Stanford to a bold question. What if one could become aware within the dream itself? This state, dubbed lucid dreaming, was once considered mystical or fraudulent. But LaBerge and others developed methods to train subjects to recognize dream signs and signal from within the dream using pre-agreed upon eye movement patterns, e.g., looking left, right, which could be recorded on the polygraph. This was a scientific triumph, a line of communication established from the isolated world of the dream back to the waking laboratory. It proved that metacognition, thinking about one's own state, was possible even in the depths of REM sleep. Lucid dreaming became a new frontier, a tool for studying volition and consciousness in a brain-dreamt world. All this intense, empirical activity did not go unnoticed by the public. The idea that science was cracking the code of dreams captured the popular imagination. It featured in magazines, television specials, and inspired artists and writers. The Dream Lab became a symbol of a new, technological approach to ancient mysteries. For the first time, the veil between the waking and dreaming self seemed to be lifting, not through interpretation, but through measurement. Yet amid this excitement, a note of caution was also sounded. Some researchers and philosophers worried that in reducing the dream to EEG traces and content codes, something precious was being lost. The ineffable quality, the personal meaning, the numinous sense of dreaming as a visit to another realm. The scientific map, no matter how detailed, might never capture the full territory of the dreamer's lived experience. This tension between explanation and experience would remain, and still does. But the dream laboratories of the 60s and 70s had irrevocably changed the game. They had brought the dream into the light of day, dissectable, analyzable, and endlessly fascinating. As the empirical study of dreams flourished, its impact began to ripple outwards, transforming adjacent fields and confronting society with new ethical and philosophical dilemmas. The dream was no longer a passive subject of study. It was becoming an active tool for understanding the mind, a diagnostic instrument, and even a potential landscape for psychological intervention. This expansion marked the maturation of dream science from a curious specialty into a significant force in the broader human sciences. One of the most profound impacts was on psychiatry and clinical psychology. The Dream Lab provided a controlled environment to study the nightmares of post-traumatic stress disorder, PTSD, the bizarre and frightening dreams in schizophrenia, and the symbolic narratives in borderline personality disorder. Researchers found that the dreams of individuals with PTSD were not just bad dreams. They were often exact, terrifying replays of the traumatic event, lacking the normal transformative quality of dreaming. This repetition compulsion in sleep suggested a failure of the normal REM-mediated emotional processing system. The dream, in this case, was not therapy. It was the symptom of broken therapy. This understanding helped shift PTSD treatment towards therapies like imagery rehearsal therapy, which actively attempts to rewrite the traumatic nightmare script while awake, demonstrating a new clinical application of dream science. Similarly, the study of dream content in depression reinforced the biological findings. The dreams of the depressed were often marked by themes of loss, failure, and rejection, with a preponderance of negative emotions and fewer familiar characters. This wasn't just a reflection of a sad mood. It was a measurable cognitive bias playing out in the nocturnal theater, providing a unique window into the depressed person's inner world that complemented daytime interviews. The rise of cognitive neuroscience in the 1980s and 90s provided dream research with its most powerful tools yet, neuroimaging. With PET, positron emission tomography, and fMRI, functional magnetic resonance imaging, scientists could now watch the dreaming brain in action. The pictures they developed were stunningly clear. The limbic system, especially the amygdala, fear, emotion, and the anterior cingulate cortex, emotional evaluation, was highly active. The primary visual cortex and associated visual association areas were lit up, confirming the brain was generating imagery from within. The prefrontal cortex, particularly the dorsolateral prefrontal cortex, DLPFC, responsible for logical reasoning, self-reflection, and working memory, was significantly deactivated. This last finding was a revelation. It provided the neural basis for the classic features of dreaming. The uncritical acceptance of bizarre events, low DLPFC activity, the emotional intensity, high amygdala activity, and the poor memory for dreams upon waking. The DLPFC is crucial for memory encoding. The neuroimaging data was a perfect marriage of psychology and physiology, showing precisely how the strange rules of the dream world were enforced by the rules of brain metabolism. Concurrently, The Discovery of REM Sleep Behavior Disorder, RBD, by Carlos Schenk and Mark Mahold in the 1980s, turned dream science into a prognostic tool for neurology. They documented that older men who acted out violent dreams, punching, kicking, yelling in their sleep, were at extremely high risk of developing Parkinson's disease or Lewy body dementia years or even decades later. RBD was a broken break in the REM system, and that broken break was an early warning sign of a coming neurodegenerative storm. Suddenly, the sleep lab became a critical front in the early detection of devastating brain diseases. This period also saw the flowering of lucid dreaming research from a curiosity into a formal discipline. Stephen LaBerge and others established the Lucidity Institute, developing techniques like mnemonic induction of lucid dreams, mild, and creating devices, dream masks, that flashed lights or played sounds during REM sleep to cue awareness. Lucid dreaming was studied not just for its novelty, but for its therapeutic potential, for treating recurrent nightmares, for physical and mental rehearsal. Athletes, musicians, public speakers could practice in dreams, and as a unique state of consciousness for exploring mind-body relationships. Yet, with these advances came new ethical questions. If we can cue and influence dreams, do we have a responsibility for the dreamer's psychic experience? If RBD predicts Parkinson's, should we tell a healthy, asymptomatic person they have a high probability of a terrible disease in the future? Does the mechanistic understanding of dreams diminish their personal meaning? And perhaps most unsettling, if we can precisely correlate brain activity with specific dream content, are we moving towards a technology of dream reading? While still the realm of science fiction, these questions began to be seriously debated in bioethics circles as the boundary between private inner experience and publicly observable brain data grew thinner. The cultural footprint of this scientific revolution was deep. It influenced literature, from the neuronovels of Ian McEwan to the speculative fiction of Philip K. Dick. Film, exploring dream states and reality in movies like The Matrix, and even the law. Testimonies based on dreams or visions were increasingly viewed through the lens of neuropsychology. The idea of a completely private, inaccessible mind was being challenged. By the end of the 20th century, the shock had settled into a rich, complex, and sometimes uncomfortable new normal. The dream had been taken apart, scanned, quantified, and modeled. Yet, paradoxically, this had not made it less wondrous. Instead, it revealed the dream to be more integral to our health, our minds, and our very brains than anyone had previously imagined. The meaning of dreams was no longer just a psychoanalytic conjecture. It was embedded in their function for memory, emotion, and brain health. The mystery had not been solved. It had been upgraded from a supernatural riddle to a biological masterpiece. The journey that began with a graduate student's perplexed gaze at a polygraph roll in a Chicago basement has led us to the brink of a new understanding of what it means to be human. We have witnessed a collision of paradigms, the birth of a new science, and the gradual integration of the dream into the very fabric of biology, psychology, and medicine. As we conclude this chapter on the shock waves and subsequent research, we arrive at a moment of synthesis, not just of scientific facts, but of what this knowledge means for the individual lying in the dark, listening to this story. The great shock to the scientific world was not merely the discovery of a new sleep stage. It was the dawning realization that consciousness is not a binary state, on or off, awake or asleep. It is a spectrum with different flavors and forms. REM sleep revealed a third mode of being, a conscious, experiencing, emotionally vibrant self, generated entirely from within, while the body lies dormant and the gates to the outer world are closed. This forced a fundamental rethink. The brain does not shut down for maintenance. It shifts state. It changes the channel from external broadcast to internal production. This understanding dissolves an ancient duality. For centuries, the mind was seen as separate from the brain, the former ethereal and meaningful, the latter mechanical and material. REM sleep research helped bridge that chasm. It showed that the most seemingly transcendent aspects of the mind, vivid hallucinatory narratives, profound emotions, a sense of presence in an alternate reality, are inextricably tied to specific, measurable patterns of flesh and blood. The dream is not a visitation. It is an emergent property. It is what a complex brain does under a certain set of neurochemical conditions. This is not a reduction, but a revelation. The material world is capable of generating the immaterial experience. The ghost is not a machine. The ghost is the machine, operating in dream mode. For you, tonight, this synthesis offers a profound form of peace. It means that the strange, the frightening, or the beautiful visions that visit you in the night are not intruders. They are expressions of your own brain's innate creativity and processing power. They are the sound of the engine running in the garage, tuning itself, sorting its parts, testing its systems. The anxiety dream is not a prophecy, but a sign of your amygdala diligently processing worry. The surreal, flying dream is not an escape, but a sign of your cognitive networks making loose, creative connections. Even the frustrating dream of being unprepared or lost is likely your memory systems organizing the day's tasks and uncertainties. This knowledge grants permission to stop trying to control or interpret every narrative thread, permission to see sleep not as a blank void between productive days, but as a productive and necessary phase in its own right. The dream is not a distraction from the real work of sleep. It is part of the real work. When you close your eyes, you are not ceasing to be. You are transitioning to a different kind of being. Furthermore, the story of this research is a testament to human curiosity itself. It is a story of how a stubborn anomaly, patiently pursued, can crack open a worldview. From Masorinsky's meticulous controls to Juvit's lesioned cats, from Dement's sleep-deprived volunteers to the modern fMRI scans, It is a chain of human effort to understand ourselves. When you sleep, you are not only benefiting from eons of evolution that crafted the REM cycle, you are also benefiting from decades of human ingenuity that deciphered it. Your rest is watched over by the ghosts of those curious, tireless researchers that as we leave the bustling halls of academic debate and the sterile glow of the sleep lab, we return to the intimate space of your own bedroom. The science has done its job. It has provided the map. Now it is time to close the map and experience the territory. Let the history fade. Let the names of researchers, the dates of papers, the acronyms of brain regions all soften and melt away. What remains is the simple, awe-inspiring fact. Your brain is about to perform its most ancient ritual. It will power down the external sensors. It will engage the internal network. It will tell itself stories in the dark. You are about to contribute your own data point to the grand human experiment of consciousness. Your dreams tonight, whether remembered or forgotten, are part of the ongoing mystery. But now you know the context. You are not a passive victim of random neural firings. You are the beneficiary of a sophisticated, self-regulating system of maintenance, learning, and emotional regulation. You are the audience of a private theater run by your own brain. Surrender to it with confidence. There is no test to pass, no meaning to extract unless you wish to. Your only task is to provide the time and the stillness. The brain knows the script. It has been performing this play since long before you were born, and it will continue its run every night of your life. Now, let the final sounds of this chapter, the hum of technology, the whispers of old dream reports, blend into a single, soothing tone. A tone that feels like the brain itself settling, like a great library quieting for the night, ready for the stories to be written on its silent shelves. We have traveled far, from the icy silence of Antarctic ocean currents to the scratch of a polygraph pen in a Chicago lab. We have followed the hidden river of the deep sea, and then turned inward to follow the hidden river of the sleeping mind. Both journeys revealed the same profound truth. Beneath the surface of our conscious days, there lies a world of magnificent, ordered, essential activity. A world that works in silence and darkness, on scales of time and complexity that humble our waking thoughts. This final chapter is not about more discovery. It is about integration. It is about coming home. Home to your own body. Home to this night. Home to the simple, miraculous fact of your own awareness, preparing to shift from the daylight channel to the nighttime channel. This is an invitation to experience everything we have learned, not as information, but as a felt sense, to let the science settle into your bones, and then to let it go, so that you may simply be the process. So, let us begin where all sleep begins, with the body. Bring your attention to the physical sensation of where you are. Feel the weight of your body pressed against the bed, the sofa, the chair. Notice the points of contact, your heels, your calves, your back, your shoulders, the back of your head. Feel the gentle, relentless pull of gravity, holding you to the earth. For tonight, you do not need to resist it. You can allow yourself to be fully supported. The earth has held dreaming bodies for millions of years. Yours is just the latest. Now, turn your attention to your breath. Do not try to change it. Simply observe its rhythm. The cool air entering through your nose. The slight pause. The warmer air leaving. Your breath is the metronome of your life, and it is beginning to slow, to deepen, as it does every night when the sun goes down. This slowing is the first, most ancient signal. It is the brainstem's command to the rest of the system. Prepare for the shift. As you listen, perhaps your eyelids feel heavy. This is not fatigue in the negative sense. It is the levator palpebrae muscles, so diligent all day in holding your eyes open to the world, receiving their permission to rest. The curtains are being drawn. The external show is ending. The internal show is about to begin. Think of the journey your brain is about to undertake. In a little while, a cluster of neurons in your pons will begin to fire rhythmically. This is not a thought. It is not a decision. It is a biological tide, as inevitable as the ocean's pull on the Antarctic bottom water. When that tide reaches its peak, it will trigger a cascade. A signal will race down your spinal cord. A polite but firm request to the motor neurons. Stand down. Take a break. Let the muscles go. This is the genesis of the paralysis that keeps you safe, that turns your bed into a safe harbor while your mind sails into its own seas. Simultaneously, that same pontine tide will wash upward, bathing your thalamus in a neurochemical soup rich in acetylcholine. The thalamus, the great gatekeeper of sensation, will respond. Deprived of new input from eyes, ears, and skin, it will do what it has evolved to do. It will generate its own signal. It will become a broadcaster of internal news. It will send pulses to your visual cortex, and those pulses will become shapes, colors, landscapes. It will send pulses to your auditory cortex, and they may become voices, music, the sound of wind. Your amygdala, the keeper of your emotional memory, will join the chorus. It will infuse these nascent images with feeling, with joy, fear, curiosity, or longing. This is not random. It is the brain's way of sorting the emotional ledger of the day, of weighing what matters, of rehearsing what frightens or delights us. And your prefrontal cortex, the diligent manager, the critic, the planner, it will grow quiet. Its lights will dim. For a few hours, you are free from its constant analysis, its worrying, its lists. This is the gift of the dream state, a vacation from the self that worries, and an audience with the self that feels, imagines, and creates without borders. This is what is about to happen, but it is not happening yet. You are in the liminal space, the hypnagogic state, the space between. This is a state of pure potential. Thoughts may drift, lose their edges. Strange, Fleeting images may cross the back of your eyelids, faces, patterns, nonsensical scenes. This is the brain's warm-up act. It is loosening its joints, testing the lights. There is no need to follow these images or grasp these thoughts. Let them drift by like clouds in a slow-moving sky. Your only task is to observe the departure from one shore, with trust that the boat knows the way to the other. As you linger in this borderland between waking and sleeping, let's deepen our surrender by visiting the different stages of the journey ahead, not as a scientist would, but as a traveler who knows the terrain. Think of it as a preview of the landscapes your own consciousness will traverse tonight. You are safe. You are guided by a biology older than memory, the first descent into the shallows of N1. This is where you are likely drifting now. Muscle tone begins to relax. The rapid alpha brainwaves of quiet wakefulness break up, replaced by slower theta waves. Your thoughts become less linear, more dreamlike. You might experience sudden, brief muscle twitches, a hypnic jerk. Don't be alarmed. This is believed to be a vestige of our primate past, a last-minute check from the brainstem as the motor system goes offline. Are we falling from a tree? No. Proceed with sleep. It is a harmless glitch in the shutdown sequence. Let it pass through you like a ripple in a pond, settling back into calm. The anchoring depth, stage into sleep. You are now officially asleep. Your awareness of the external world fades. Your brain produces two distinctive electrical signatures, sleep spindles and K-complexes. Sleep spindles are brief bursts of faster brainwaves. Think of them as neural whisks that help mix and consolidate new memories, whisking them from a short-term holding area into long-term storage. K-complexes are large, slow waves that act as gatekeepers, suppressing arousal to external sounds, a slamming car door, a distant siren, so you can stay asleep. They're your brain's internal noise-canceling headphones. As you hear my voice now, if you are drifting, your brain may be generating K-complexes to gently dampen it, allowing you to go deeper. This is good. This is the system working. Allow it. The deep well, slow wave sleep, and 3. This is the most restorative phase. Your brain waves become large, slow delta waves, rolling through your cortex like deep ocean swells. This is physical repair time. Growth hormone is released. Tissues are regenerated. The immune system is fortified. Your conscious mind is far away. There are few dreams here. Only a profound, blanketing quiet. This is sleep at its most elemental. It is the brain dipping into a deep, cool spring of restoration. You will spend more time here in the first half of the night. And then, the ascent, the return journey, and the turn to REM. After perhaps 70 to 90 minutes of this deep dive, your brain will begin to climb back up, through N2 again, but instead of waking at the surface, it will make a turn, a different path. The brainstem's REM-on cells will fire. The command for muscle paralysis will be issued. The thalamus will switch to its internal broadcast mode, and you will arrive at the first REM period. It will be short, perhaps only 5 or 10 minutes. The imagery might be fragmented, vague, but the engine has started. The projector in your private cinema has whirred to life. The first tentative images are on the screen. This cycle, descent into deep sleep, ascent into REM, will repeat. As the night wears on, the deep sleep and 3 periods will get shorter, and the REM periods will grow longer, richer, more narratively complex. Your final REM period, just before dawn, may last 30, 40, even 50 minutes. This is where you have your longest, most vivid, most memorable dreams. It is the brain's grand finale before the curtain of waking rises. Now, knowing this map, you can release all effort. There's no need to steer. You are on a train with a predetermined, perfect schedule. The switches are thrown by your brainstem. The landscapes pass according to a timeless itinerary. So, as you feel yourself slipping deeper now, past the hypnic jerks, into the embrace of stage N2, you can offer a silent thanks to the systems at work. Thank the spindles for weaving your memories. Thank the K-complexes for guarding your peace. You are entering the care of an ancient, automatic intelligence. Let your awareness now settle not on thoughts, but on sensations. The slight, cool feeling of air on your cheek, the heaviness in your limbs, the distant, rhythmic thrum of your own heart. These are the anchors of the physical self, and they are becoming distant bells, ringing from a shore you are gently floating away from. The train is moving. The lights of the waking city are receding. You are heading into the quiet, rolling hills of deep sleep. There's nothing to do on this journey but be a passenger. Look out the window at the passing dark. It is not empty. It is full of the invisible work of restoration. We now arrive at the heart of the night. The deep, slow wave restoration is underway. But our journey as observers takes a speculative, imaginative turn. For while your body is immersed in the delta wave ocean of N3 sleep, we, as the silent narrators of your journey, can turn our gaze to the wonder that is cycling in the background, the REM state, being prepared, like a stage being dressed in the wings. Imagine, if you will, the brain not as a machine, but as a vast, dark, and ancient city. In the deep of night, most districts are quiet, lights dimmed. But in one particular, old neighborhood, the brainstem, a special festival is being prepared. This is the festival of the dream. The stage managers are the REM cells in the pawns. They are lighting chemical lanterns, acetylcholine, signaling that the festival is about to begin. Their first act is to send messengers running down every street leading to the spinal cord, hanging signs on every muscle. Closed for renovation. Do not disturb. This is the atonia. The city's movement is stilled, so the festival inside can proceed without the city itself stumbling around. Next, they send a delegation to the thalamus, the city's central communication hub. stop receiving outside news. They instruct. Tonight, we generate the news from within. The thalamus nods, switches off its external antennas, and fires up its internal generators. It begins to send out bulletins of pure, unfiltered signal, not of the real world, but of potential worlds. These bulletins flood into the visual district, the occipital cortex. Architects and artists there, with no blueprints from the eyes, start building from the signals alone. They construct impossible buildings, familiar faces with strange features, landscapes that bend and melt. It is abstract expressionism rendered in neural code. In the emotional quarter, the limbic system, especially the amygdala, the festival takes on its mood. The signals from the thalamus are colored here with feeling. A bulletin about a hallway becomes infused with dread. A signal about a friend is washed in joy. The amygdala is the festival's lighting director, bathing everything in deep hues of emotion. Meanwhile, in the executive towers of the prefrontal cortex, the lights are mostly off. The mayor, the planners, the critics, the logicians, they are asleep at their desks. This is crucial. With them offline, the festival has no rules. Physics is optional. Time is elastic. The self is fluid. You can be yourself and someone else and an observer, all at once. This is the source of the dream's freedom and its bizarreness. And what of the rapid eye movements? Imagine them as the flickering of 1,000,000 candles held by the audience in this internal festival, their flames darting as they follow the action on the stage of the mind. Or perhaps they are the usher's flashlights, sweeping across the neural aisles, checking on the proceedings. This festival is not chaos. It is constrained chaos. It is the brain operating under a different set of rules, a different chemical governance. It is a state where memory fragments are recombined, where emotional tones are adjusted, where new neural connections are tentatively tried out. It is where a musician might find a new melody, a scientist a new connection, a troubled heart a new perspective on an old pain. You are not in this festival yet. You are still in the deep, quiet part of the night where the city rests. But this festival is being prepared for you. It will happen, whether you remember it or not. Your brain will hold this festival for itself, because it needs to. It is part of its ecology, part of its health. So, as you rest in the profound quiet of deep sleep, know that creativity is incubating. Know that emotions are being sifted and settled. Know that memories are finding their permanent shelves in the library of your mind. The night shift is on duty, and it is doing the work that the day shift could never do. This perspective allows for a beautiful reframing. That strange dream you had last week, it wasn't nonsense. It was a report from a festival, a snippet of the brain's internal processing, translated into a story you could almost understand. The forgotten dream, the festival still happened. You just didn't keep the program. Now, let this understanding dissolve any last remnants of performance anxiety about sleep. You are not failing if you don't remember your dreams. You are not doing it wrong if you wake up briefly. The process is robust. The festival will go on. The deep restoration will occur. The cycles will turn. Your trust can now become complete. You are in the hands of a system that has perfected its craft over hundreds of millions of years of evolution. From the first amphibian that slept with half its brain at a time, to the complex, cycling brain of the mammal you are, this process has been refined, conserved, and cherished by life itself. You are not just sleeping. You are participating in a biological ritual of immense antiquity and importance. You are connected to every dreaming creature that has ever lived. In your sleep tonight, you are as ancient as the first dreamer. The deepest part of the night is passing. The long, restorative troughs of slow-wave sleep are becoming shorter. The balance is shifting. In the brainstem, the REM cells are gathering their strength, their chemical signals rising like a tide against the receding shore of deep sleep. The first festival of the night has been quiet, brief, but now the stage is being set for the main performance. The longest REM period approaches, the one that often cradles the most vivid dreams, the one that lingers at the threshold of morning. But you, the listener, are likely far from that now. You are somewhere in the middle cycles, in the gentle sway between depth and descent. Perhaps you are even hovering closer to wakefulness, listening to the end of this story. This is perfect, for this final chapter is not about leading you into a dream, but about giving you something to carry into all your nights, a sense of peace, understanding, and belonging. Let us consolidate the gift of this knowledge. First, the gift of perspective. The worries of the day, the lists, the conflicts, the anxieties, they are the surface weather of your mind. But you are not just the weather. You are the climate. And the climate of your mind is regulated by these deep, nocturnal cycles. The REM sleep that will patiently process today's emotional weather. The slow-wave sleep that will repair the wear and tear. Knowing this allows you to take the long view. A bad day is just a data point for the overnight processing system. Trust it to do its work. Second, the gift of sanctuary. Your bed is not just a piece of furniture. It is a portal. Every night, you leave the consensus reality of the waking world and enter a private, sovereign state, the state of dream. Its laws are different. Its landscapes are yours alone. In a world that often demands constant connectivity and external validation, this is your ultimate privacy, your unassailable inner sanctuary. No one can invade your dreams. They are the last truly private space. Honor that. Protect the time you need to travel there. Third, the gift of connection. When you dream, you are speaking a language older than words. You are using the native tongue of the mammalian brain. In your dreams, you are kin to a sleeping cat twitching its paws, a dog whining in its sleep, a whale slowly cycling through sleep states in the vast, dark ocean. You are participating in a rhythm of life that transcends species. That flutter beneath your eyelid? It is a cousin to the movement in the seal pup's eye as it dreams of swimming. This connects you to the living world in a silent, profound way. Now, as we prepare to leave this narrative and return you to the quiet of your own night, let us perform a final, gentle unlinking. Feel the weight of your body one more time, heavier now, more fully surrendered to gravity. Listen to your breath. Slower now, deeper, a tide pulling you inward. Acknowledge the faint tingling in your hands, your feet, as circulation slows and the periphery of your body softens into the background. Now, one by one, release the concepts we have explored. Release the image of the Antarctic bottom water, the silent river. Let it flow on without your thought. Release the picture of the Chicago lab, the polygraph pens. Let them fade into history. Release the diagrams of the brainstem, the pons, the amygdala. Let the biology simply be, without your mental supervision. Release the theories, activation synthesis, memory consolidation, emotional regulation. Let the process work without the label. What remains when all the concepts are set down? Sensation, the coolness of the sheets, the rhythm of breath, darkness, behind your eyelids, a universe of potential, trust, a deep, wordless knowing that the system is operational, that the cycles will turn, that the festival will be prepared, whether you attend consciously or not. This trust is the ultimate goal. It is the opposite of insomnia's anxiety. It is the calm of the deep sea, moving according to laws older than fear. So I will now be quiet. The story is told. The map is drawn. The train is on its tracks. My voice will fade, and you will be left with the sound of your own being, preparing for the next turn of the wheel. There's no need to wait for anything. No need to listen for a cue. Sleep is not something you fall into. It is something you allow. You are already allowing it. The very act of lying still, listening, is the permission slip. Let my words become like distant wind chimes, their meaning dissolving, leaving only a soothing sound. Let that sound become part of the room's ambience. Let the ambience become part of the darkness. Let the darkness become part of you. You are ready, not because you have understood everything, but because you don't need to. The most sophisticated knowledge is knowing when to stop knowing and simply to experience. The night is yours. The silent river within you flows. The dark cinema awaits its audience. Go in peace.